Hey guys, Miss Marissa here, and in this video I'm going to talk to you all about solubility products, or KSP. These problems work exactly like all the other equilibrium problems we've been working. We're still going to have rice tables, we're still going to be writing equilibrium expressions. The only difference is that now we're going to be doing this with ionic compounds. Now I have to preface this whole lesson by saying that technically, this includes both in pre-P and AP. We've kind of been lying to you guys. We've always said that ionic compounds are either soluble, they will dissolve in water, or that they're not soluble and they will not dissolve in water. Well, that second category of things that don't dissolve in water technically can an itty-bitty little bit. Not enough where it would factor into a chemical reaction, but enough that if we're writing an equilibrium expression, we can include it in that process. So just as kind of a reminder about which salts are considered soluble and which ones aren't, these are our solubility rules that we've been using since pre-AP. For the AP test, you're responsible for knowing that all group 1 ammonium and nitrate compounds are soluble. But if you notice on this table, all those exceptions that we see over here, all these insoluble compounds that we see over here, these are the kinds of compounds that we're going to be working with in our problems today. Again, if you had these compounds in, say, a net ionic equation process, you would not split them apart. You would leave them together. They would be your solid precipitate in that reaction. But when it comes to equilibrium, now we're going to be allowed to split them apart. So we just want to be very careful that with these insoluble compounds that we're only splitting them apart if we're doing one of these equilibrium processes with KSP. So just kind of pay very careful attention to what situation you have. If we do see it's an equilibrium expression situation, here's the type of equation we would write for the dissolving process. If you notice, this looks exactly like the dissolving process of soluble ionics, with one big exception. We do see a double arrow being used instead of a one-way arrow. We're still breaking up into ions, we're still putting charges, we're still putting states of AQ, so that part of it hasn't changed. We can then write our equilibrium expression here. Instead of being called that, it's called a solubility product expression. It's the same format that we've been working with, products over reactants. But you notice here that they've only included the products as part of this. Now let's think about why for a minute. If you think back to one of our first days with working with equilibrium expressions, there were certain states that didn't get included into these formulas. And those were states that did not have a concentration, did not have a molarity to them. So what that means is pure liquids would not get included into this, nor would, hint, hint, solids. So if you notice here, our AXBY, the thing that's representing our ionic compound, is a solid. And so we don't see this over that reactant here on our equation. So it asks down here, why was the original substance, the AXBY, not shown in the KSP expression? Again, solids are not included in equilibrium expressions. Whether it's a KSP or any other kind of equilibrium expression. We got to be really careful there. By the way, did y'all see the funny joke at the bottom? This is a salt. It's NaCl, table salt. Isn't that cute? Oh, gotta love a good joke. Okay. On the next page, what we're going to do is we're going to start the process of seeing how we can use all of our information in a rice table for KSP. There's one term I want to talk about for just a second before we do our math, and that is this term here called solubility. It says solubility is defined as the quantity of a solute, an ionic salt, that dissolves in water to form a saturated solution. So when our solution is considered saturated, what's the maximum amount that I would be able to dissolve? We're going to actually be able to calculate that value with our problems, or sometimes our problems will give us that value. We're going to have to be careful, though, with what unit it's given to us in. I will warn you that there are some AP problems, especially in the multiple choice, where they will use the variable S to represent solubility. I tend to, instead of using S, I will just use the same X like we've been using in rice tables, only because, as y'all remember, entropy also uses S, and so I think that it gets kind of confusing with which S are we using here. So just kind of be aware of the context of your problem if you see that S being used. As far as the units are concerned, sometimes you will see grams per liter. Sometimes you will see moles per liter, molarity being used. Remember, in a rice table, we want to typically use molarity, moles per liter, unless we have gases and we're given pressure. That would be the only kind of exception to that rule. So if they give us this grams per liter or ask us for grams per liter, a lot of times we're having to convert to that unit because we'll normally have molarity from the rice table itself, okay? There are, oh, by the way, there are some steps here. If you get lost or stuck on your practice and you want something to kind of use as a general guideline, this would be great. I'm going to just jump into a problem and kind of talk about those steps as we go along here. So on this problem, it says, hey, when silver sulfide dissolves at 25 degrees Celsius, the equilibrium concentration of silver ion is 5.8 times 10 to the negative 17th molarity. What is the KSP of silver sulfide? So if I actually checked silver sulfide on my solubility table, I would actually see that this is an ionic compound that doesn't normally dissolve. So the reason why they're giving me this KSP here, or excuse me, why they're asking me for KSP, is because this is one that is only going to dissolve a little bit. Okay, and so that's why I'm allowed to calculate. Since it's an equilibrium problem, I'm going to go ahead and set up my traditional rice table. It's out of habit. I just kind of go ahead and set that up immediately. I'm going to start off with my dissolving equation, my reaction here. I have Ag2S. Okay, we're going to assume that that is a solid to start off with. Since this is an equilibrium problem, I'm going to put a two-way arrow. I know that silver is +1 as an ion, but there were two of them to balance out in this equation, so I'm going to put that 2 in front as a coefficient. And I'm going to have sulfur at -2, and that is going to be, ooh, AQ as well. Mercy. All right. By the way, you notice that looks exactly like the dissolving equations that we've been writing up to this point. It's no different, except that now we have a double arrow instead of a one-way arrow. Since I'm going to solve KSP, I'm going to actually go ahead and write a KSP expression as well. My KSP expression for this would be my two products. Okay, so the Ag +1 raised to its coefficient, and the S2, -2, excuse me, raised to its coefficient of 1. Normally I would have this over reactants, but as a reminder, our reactant here is a solid, and so therefore it would not get included in this expression. All right, so I want to solve KSP, which means I need to plug in these concentrations here. I need to know what they are, and the only one that they've told me so far is that the equilibrium concentration of silver ion is 5.8 times 10 to the -17th molarity. And it is a molarity, so I can go ahead and plug it into my rice table. But notice I did it with the E because this is at equilibrium. So I need the concentration of this other guy here. Well, I know that in this equation, I'm not plugging anything in with Ag2S. So to be honest, I don't really care what's going on over here. It doesn't really make a difference. So I kind of scratch that side out. And I want to think about this side over here. I know originally before this dissociated that these both would be 0 and that they would both go up in concentration as this dissolving progressed. Well, this one would go up by some 2x, whereas this one would only go up by some x, some 1x value. So if this went up by 2x and is now 5.8 times 10 to the -17th, and this only went up by 1x, I can now use this information to figure out what concentration of sulfide ion I have at the end. So again, if this went up double and this only went up half of it, in order to get what number goes here, I would need to take that 5.8 times 10 to the -17th and divide it by 2. There's a 2-to-1 ratio between those ions at the end. So this guy at the end would have been 2.9 times 10 to the -17th molarity, or half of this 5.8 number over here. So now that I have those two concentrations, now I can plug them into my KSP expression. So I'm going to have the Ag at 5.8 times 10 to the -17th. That's going to be squared. I'm going to have the sulfur at 2.9 times 10 to the -17th. And that's going to be raised to the first. And now I'm just going to plug that in my calculator and see what it gives me. Now, as far as sig figs are concerned, since the concentration they gave me had 2 sig figs, I'm going to show 2 sig figs in my answer. So I'm going to show 9.8 times 10 to the -50. By the way, KSP does not have a unit. It's unitless. It's just a ratio of reactants and products. Also, you notice this number is incredibly small. I mean, 10 to the -50 is a decimal, 49 zeros, and then our 98 number, okay? That is because 99.999% of this ionic compound is staying together, and very little of it is actually dissolving into ions. So what you're going to notice about these KSP values is that typically, if you're doing one of these types of problems, the value is going to be incredibly small for that KSP. All right, let's look at another one here. It says, hey, I have bismuth sulfide, which has a solubility of 1.0 times 10 to the -5 grams per liter at a particular temperature. Calculate its KSP value. So again, I'm wanting to solve KSP here, except that I noticed that they're giving me a little bit of different information than what we saw in the previous problem. So I'm going to start this off, though, just like I started off the previous one. I'm going to start off with a rice table here. I know I have the Bi2S3 to start off with, and that is going to start off as a solid. Now, as far as my ions are concerned here, I kind of need to use the sulfur to figure out the bismuth charge. They kind of left something out on the name here for this guy to make us work for it, if you will. If I think about this, we just said that sulfur a minute ago was a -2, and there's 3 of those ions in play here. So if I want to figure out what charge the bismuth is going to be, I know that there's going to be 2 of those bismuths that are going to need to balance out the 3 -2s from the sulfur. So the only thing that bismuth could be here is +3. And it too would be aqueous. All right, so now I notice that they give me a solubility value. So something a little bit different than what we saw a minute ago. What they're telling us here is how much of this ionic compound is dissolving. They're telling me essentially on this C here how much of it is being lost. I had some amount to begin with. I don't know what that amount is, but I know that the amount that is dissolving is this 1.0 times 10 to the -5 grams per liter. I know that this is what goes here. Now, here's the deal though. What I want to solve is KSP. KSP is going to be the bismuth +3 raised to an exponent of 2, and the S -2 raised to an exponent of 3. Again, the solid does not get included in my formula here. So what I really need are those ending concentrations of the bismuth and sulfur, okay? But if I think about the rest of this rice table for a minute, okay? These starting off at 0, this going up by some 2x value because there's a 2 in front of it, this going up by some 3x value because there's a 3 in front of it. If I know this value of x here, I also know the value of x for these, which means I can then use that information to plug into my KSP. So what we need to do is we need to put this into a unit that's helpful. If you notice right now, it's in grams per liter. If it had been in moles per liter, molarity, I could have just used it as is and multiplied it by 2 to get this guy, multiplied it by 3 to get this guy. But in grams per liter, that's in a unit that's not totally helpful to us. So what I'm going to do first is I'm going to take it, that grams per liter, and I'm going to convert it into moles per liter. My grams on top would be canceled out if I put it on bottom, and I want to take it into moles. And again, I'm doing this for the Bi2S3. Okay, which means I need the molar mass of Bi2S3. Now, I happen to have that value here. It is a big one. It is 514.17 grams per 1 mole. And when I plug that in, that gets 1.9 times 10 to the negative 8th moles per liter. So here's the deal. This value here is how much of that Bi2S3 is actually dissolving. It is X. So now, if these other values are 2X and 3X, the bismuth concentration at the end is simply going to be 2 times the 1.9 times 10 to the negative 8th. And the sulfur is going to be 3 times that 1.9 times 10 to the negative 8th. And now I have my concentrations to plug into KSP. So here we go. This 2 times 1.9 times 10 to the negative 8th, that gets a value of 3.8 times 10 to the negative 8th. So again, this comes from there, but don't forget it is squared in the KSP expression. Our 3 times 1.9 times 10 to the negative 8th gets 5.7 times 10 to the negative 8th. But again, that is going to get cubed. Okay, so it gets doubled and tripled here, but then it also gets squared and cubed here. So kind of keep that in mind. And so my final KSP value ends up being 2.7 times 10 to the negative 37. Whoops, that has a negative with it. Sorry, kind of made my box over it, didn't I? So again, KSP is unitless, so that would be your answer. Again, it's incredibly small because, again, very little of this is actually going to product. 99.99% of it is staying as the reactant, as that solid. All right, let's see a different type of problem now. On this particular problem, we were given solubility and asked to get to KSP. The ones on the next page are exactly the opposite. I'm going to be given KSP and asked to find the solubility. We're going to approach it, though, kind of from the same perspective here with a rice table and setting up an equilibrium expression. So, surprise, surprise, guess what I'm going to set up first here? A rice. It tells me, hey, I have copper 2 iodate. Copper is Cu. If it's going to have a +2, the iodate, IO3, is -1, so I'll need 2 of those to cancel out the copper's charge. That is solid. I'm going to put my double arrow for my equilibrium. We're going to have copper +2, aqueous, and then we're going to have 2 of the IO3s, the iodates. By the way, notice that I don't break up a polyatomic ion further when I do a dissociation. The polyion stays together, but if I needed 2 or 3 or 4 of that polyion, then that would get brought in front as a coefficient. All right, I'm also going to go ahead and set up my KSP expression. It is going to be copper +2 raised to an exponent of 1 because of a coefficient of 1. And then the IO3, -1, with the exponent of 2. They actually give me KSP, so I can kind of use that to figure out what these ions are. Now, let's talk about what they're really asking me to solve here. They are wanting us to solve the molar solubility of the salt, which is going to be molar solubility in terms of molarity or moles per liter. What that means is they're asking me to calculate how much this goes down by. How much of this copper 2 iodate is actually dissolving. That is what they're asking me to find. But to figure that out, I'm going to need to figure out what X is based on utilizing the information from these other ions and from using KSP. So to kind of finish filling out this rice table here, I'm not going to worry about the rest of the solid information because, again, I'm not really calculating with that per se in my KSP expression. I know these start off at 0. I know this is going to go up by some x. This is going to go up by some 2x because, again, of the coefficients here. So at equilibrium, I'm going to have x of the copper. I'm going to have 2x of the iodate. And now I'm going to use that to plug into KSP. They told me the KSP value was 1.4 times 10 to the negative 7th. The copper is x. The iO3 negative 1 is 2x. But you notice that it is squared. So to kind of consolidate here, the biggest mistake I see people make on this one is they forget to apply this squared to the 2. So when you kind of reconsolidate here, don't forget 2 squared does end up being 4. And then I'll have this x times the x squared. So that's going to give me x cubed for the 1.4 times 10 to the negative 7th. To solve x, what you would need to do is, of course, divide both sides by 4. To undo the raised to the third, you could cube root it. Or remember, cube rooting is the same thing as raising both sides to the third. So you could kind of do that either way. That ends up getting an x value of 0.0033. And again, I'm going to maintain 2 sig figs based on the KSP value that they gave me. So let's talk about what that value is. Obviously, I could use this value to go solve these ions, and we'll do that here in a minute. But what I was really trying to find on this problem is the molar solubility. How much of this substance dissolved? Well, if X is equal to 0.0033, what that means is that 0.0033 moles of that CuIO32 dissolved per liter of solution. So that is my molar solubility. Okay, now the next part of the question asks, hey, what is the concentration of each ion at equilibrium? Well, I know that copper concentration is equal to X. Well, we just figured out that the X is 0.0033 molarity, or moles per liter. You could write it as moles per liter, or you can write it as molarity, totally up to you which unit you want to use. So there's my concentration of copper. My iO3, on the other hand, was 2x, according to my rice table, and so it's going to be double that value, so 0.0066 molarity for its ending concentration. Okay, so look, just by having KSP up here, we were able to solve both the molar solubility of the ionic compound to begin with, as well as get our concentrations of our ions at the end. So we were able to figure out quite a bit here. There's one other thing we could solve, and that is it asks, hey, what would be the solubility of the salt in terms of grams per liter? So we just solved moles per liter up here. So if I wanted to get the moles per liter into grams per liter, I could set up a conversion of the moles into grams. Again, to do that, I would need my molar mass of specifically the CuIO32 to do that. So if moles were up here, that means moles are going to go down here to cancel, and I'm going to have grams. The molar mass of the copper 2 iodate is another big one, 413.35 grams for every 1 mole. And once I plug that in, that gets a value of 1.4 grams per liter of the CuIO32 will dissolve. So again, what that means is that if I throw in copper 2 iodate into a vat of water, only 1.4 grams is going to dissolve in an entire liter of water, which is hardly anything. But again, that backs up the fact that this salt, for the most part, 99.99% of it, is insoluble. It won't dissolve. Only a very small amount of it will actually dissolve. And we could actually tell that based on having this very small KSP value to begin with. The fact that this is less than 1 means that we were very heavily reactant favored, and so most of my substance was staying together as this ionic compound. Very little of it was actually going and making product. All right, so let's talk about our last type of problem here. This is actually a really common type of problem to see in a multiple choice style question. Not that you couldn't see it in an FRQ question, just it's more common in a multiple choice. They actually want us here to kind of estimate salt solubility of 2 compounds given KSP information. Now, we have to be really careful here. We have to pay careful attention to whether or not the mole ratios are the same for each of the 2 substances. If they are the same, then it's actually very easy to tell the answer. If they're not the same, I kind of need to think through some mental math in order to get my answer, okay? So to see that in action here, this first one says I have calcium fluoride and magnesium fluoride, okay? So you probably wouldn't have to go through all the work that I'm about to, but I want to go ahead and show you why these problems work the way they do. So I have calcium fluoride, CaF2, starting off as a solid. I'm going to have calcium plus 2 ions, and we're also going to have 2 fluoride ions. And they tell us that calcium fluoride has a KSP of 4.0 times 10 to the negative 11th. Okay, so I'm going to come down here and say, hey, I got a KSP of 4.0 times 10 to the negative 11th, but I want to think about the molar solubility, which one would dissolve more. So remember, that's how much I'm losing of this guy. So I need to kind of figure out my X, okay? I know that this would have gone up by 1x, so this would have been x at equilibrium. I know this would have gone up by 2x, so it will be 2x at equilibrium. So when I plug in my values here to a KSP, I would have x times 2x squared. Again, squared because of that 2, and this only had a coefficient of 1, okay? Which means here that the 4.0 times negative 11th would be equal to 4x cubed. Okay, let's go through the same process now for the MgF2. Okay, so I'm going to go back and forth here. Oh, I forgot to put that was a solid. I'm going to have magnesium plus 2 aqueous. I'm going to have the 2 fluorine, negative 1 aqueous. And again, I'm trying to find that molar solubility so I can compare which one's more soluble. Here, the KSP for this guy is 6.4 times 10 to the negative 9th. And so that would be equal to, again, x for this guy, 2x for this guy. So I end up with that giving me 4x cubed. Okay, so now let's think here for just a moment, okay? If X is my molar solubility, how much of my compound is dissolving? That means the thing that would give me a larger value for X would be more soluble, okay? Well, here I have a smaller number equal to 4x cubed. Here I have a larger number, because negative 9th is a bigger decimal than negative 11th. So I have a bigger number equal to 4x cubed. So what that means is, I mean, you could go and solve the math if you wanted to and actually get your x. But what that means is that this guy would give me a larger value for x. So the larger KSP here gives a larger value for x, which means it is more soluble. So that means my winner chicken dinner here is the MgF2. The MgF2 is a more soluble salt. However, I want to make sure I'm very clear about something here. The reason why I could just look at KSP and know the answer is because I had the same anion to cation ratio. The anions, the negative ions were 2. The cation, the positive ion, was 1. I had a 1-to-2 ratio between those. So because that ratio was the same, what that meant is this side of the equation was the same. And so whichever value of KSP was bigger would ensure a bigger value for X, which would ensure that that particular salt is more soluble. Okay. So up here it states, if I have KSP values, I can infer relative solubilities for salts with the same cation to anion ratio. The larger the KSP, the more soluble it will be, which kind of makes sense because more KSP would mean that it's more product favored, right? Okay. However, if those two are not the same, I've got to be really careful with the information that I'm given if the anion to cation ratio is not the same. So let's look at this one. Now, I'll be honest, this one uses calcium fluoride again from up here. So I'm not going to reset this one up. Okay, I'm just going to write the, hey, for the CaF2, okay, the 4.0 times 10 to the negative of the 11th would equal 4x cubed. Okay, so I'm just going to kind of rewrite that from up above. Okay, but I am going to go ahead and set this up for silver chloride. Let me pick a color here. All right, so I got AgCl. It would start off as a solid, going back and forth between Ag plus 1 and Cl negative 1. And they gave me a KSP for that guy of 1.8 times 10 to the negative 10th. Okay, so if I think through this, if I want to again figure out the solubility, I'm trying to figure out, hey, what is this loss here? What is that X? Here, this is just going to be going up by X and X, right? Okay, because it's a 1-to-1 ratio. So what that means is this KSP here is going to be equal to X times X, or simply just X squared. Okay, so now let's think through here for a second. I'm actually going to go ahead and calculate some X values here. This one, if I divide by 4 and cube root, gets me an X value of 2.15 times 10 to the negative 4th. This one gets an X value of 1, once I square root both sides, an X value of 1.34 times 10 to the negative 5th. Okay, so notice a few things. Bigger X, right? If it's a bigger X, then that means more of it dissolved, and so therefore the CaF2 is more soluble. And again, it's because it's a 10 to the negative 4th versus a 10 to the negative 5th, and so it's because the amount of solubility is greater. However, if you had been tempted to just look at KSP, you would have gotten this question wrong. If you go look at the KSP values, CaF2 was 4 times 10 to the negative 11th. AgCl was 1.8 times 10 to the negative 10th. This actually had a larger KSP value than CaF2 did, which you might be tempted to think, oh, larger KSP means, oh, it's going to make more product, and so therefore it's more soluble. But notice, because the ion ratios weren't the same, when I actually go and calculate X, when I actually go and calculate the amount of solubility, I actually found that this other one gives a larger solubility value. So you want to be really, really careful when you see that the ion ratios aren't the same in your two compounds. This one had a 1-to-2 ratio. This one was 1-to-1. So if the ratios of cation to anion are the same, the one with the bigger KSP in this case here, the MgF2, that would have been your more soluble one, okay? But if the ion ratios are not the same, then do a quick calculation for your X to really see who ends up being the most soluble. All right, hope that helps. If you have any questions or have any comments, please feel free to email or contact me. Have a good day, guys. Bye.